Here we want to find the derivative of the function, but this time I've used a different notation. I've said y is equal to the root of x plus 1. If I get this notation, then I must stay with the same notation, and you might remember that the derivative is going to be dy dx. So here I write my derivative, dy by dx, is going to be equal to the limit, as h tends to 0, of f of x plus h minus f of x all over h. You can see that the formula that I'm using is still the same, so it's only my notation for the derivative that changes. So dy by dx, substituting in so that I can find f of x plus h, I must change the x to an x plus h. In other words, I'm going to have the square root of x plus h plus 1. And minusing f of x, I minus the original expression, which is x plus 1. And this is all over h. Now, can you see that it seems as though you have a problem? Because there's no h that you can take out as the highest common factor, and it seems very awkward for you to now start simplifying. But do you remember that if you wanted to get rid of your roots, you could introduce the conjugate. As you've got two terms separated by a minus, I'm going to times them by the same two terms but separated by a plus. You cannot only do this in the numerator, because then you would change the value of your expression, but by timesing the numerator and the denominator by the same number, I'm effectively timesing it by 1. So in the numerator, I'm going to times it by x plus h plus 1 plus the root of x plus 1. And then likewise in the denominator, I'm going to times it by the same thing. So that must also be times by the root of x plus h plus 1 plus the root of x plus 1. Now the trick that I'm going to tell you over here is multiply out your numerator by multiplying out those two binomial brackets, but don't bother to multiply out your denominator, because your h factor is still the problematic factor, and if I can get rid of that on its own, I have managed to eliminate my problem. So continuing to find the derivative of this function, as h tends to 0, and multiplying out my numerator, the root times the root is going to give me x plus h plus 1. The middle two terms cancel out, and then I have minus x plus 1. In my denominator, I still have h times by that long bracket factor of x plus h plus 1 plus the root of x plus 1. You can see now, looking at your numerator, there are a number of terms that are going to be able to cancel out. When I add like terms in my numerator, x and minus x add up to 0, as do 1 and minus 1. All I've got left is an h in my numerator, and if I cancel that h factor with the h factor in the denominator, I'm left with the following expression. You might have noticed when I started writing that we already have eliminated our problem, because now when I introduce 0 in the place of h, it no longer gives me a 0 denominator. And so the derivative of y in the variable x is in fact going to be given to me by the expression of 1 all over the root, of x plus 0 plus 1 plus the root of x plus 1. In other words, simplified, the derivative for this expression is going to be given to me by 1 all over 2 times the root of x plus 1. Now this looks quite complicated, so let's go and take a look once again what it would look like if I saw it diagrammatically. What I've just worked out is the expression that I would use to find the gradient of the tangent exactly when x is 3. So if I find x is 3, and I now draw a tangent exactly there, let's take a look and see what the gradient would be of this tangent. This tangent would have a gradient of 1/4. So if we take a look back at the working that we did before, let's see that if I substituted 3 into that expression, would I have got 1/4 for the gradient of this tangent? So now, the gradient of the tangent to my graph exactly when x was 3 would have been given to me by 1 over 2 times the root of 3 plus 1. So the derivative, which is the gradient of my tangent, which I showed you very nicely in the sketch just now, is going to be 1 over 2 times 2, which is 1/4. You've now just very successfully, using the definition, found the gradient of the tangent to that curve exactly when x was 3.